everybody, it's Miss Phoebus, and I'm back with another lesson, lesson 57, exponential growth and decay word problems. I know they're your favorite, they're mine. All right, so we are going to construct exponential equations given a description of a relationship. They're going to give us some information in word form, so we're not necessarily going to get points or a graph or anything like that, or even a table. We're just going to get a description in word form, and we have to build an equation based off of that. All right, and then here are our standards for today. So we are writing a function that describes a relationship between two quantities, and exponential functions are there. And we're also constructing exponential functions based off of our description of a relationship. Now remember that you have on the end of course, you have a formula sheet, and on that formula sheet you have all of these things that we're about to look at, these equations, these formats. So you do not have to memorize them, but you do have to know which ones to use and when to use them. All right, so let's do a quick review of exponential growth and decay. So what I want you to do is I want you to, when I go ahead and tell you to pause the video, I want you to label this growth, and then I want you to do a quick sketch of what an exponential growth function would look like, and then over here I want you to do a quick sketch of what an exponential decay function looks like. We're going to focus on quadrant 1 because we want our x values to be positive and our y values to be positive. So go ahead and pause the video and sketch each of those functions now. All right, so an exponential growth function is going to start off kind of low. It's not going to touch the x-axis, and it's going to take off and it's going to go way up really, really fast. Somebody sent me a cool meme, and it said, that escalated quickly, and that is definitely the description of an exponential growth function. All right, exponential decay is going to start up really, really high, and it's going to kind of flatten out close to that x-axis, but not actually get there. So how did you do? All right, so one other thing that I want to add to these pictures is about our b value. Remember, our b value is that piece is being raised to the x for growth. B has to be greater than 1. Even just a little bit bigger than 1, it's going to be a growth. And then our decay function has to be between 0 and 1. And we're going to use that today because we're going to write exponential growth equations and exponential decay equations. And if we write an exponential growth equation and the b value isn't bigger than 1, it's really a decay. And if we write an exponential decay function and it isn't between 0 and 1, it's really a growth. So we have to make sure that when we plug these numbers into our equations, we're plugging in the right number and not mixing up a growth and a decay problem, because it's really easy if you're just looking at the numbers and just throwing things into an equation. We want to make sure we're writing the equations properly. All right, so you actually have 3 formats that we can fall into. Now, the very first one is what we used yesterday. We looked at y equals a times b to the x, and we plugged in a and we plugged in b. Remember that a is our initial value. Initial meaning starting, so initial or starting amount. Now, these 3 all can be, basically they're all going to end up looking the same. It's just how do you, what kind of information are you going to be given? So the thing with B, we're going to use this setup if we're given words like half or double or triple. Okay, so if they say, hey, you have a population of otters, and it starts with this amount, and it is doubling every year, you are going to go to this y equals a times b to the x, and double means we're multiplying by 2, so b should be 2. Triple means multiply by 3. Half means multiply by half, right? Cut in half. So it depends on the wording of the situation, which format you use. So if you are running across words that say half, double, triple, quadruple, multiplying by 4, you're going to want to use y equals a times b to the x. It's going to be so much easier for you. All right, for these 2, we're going to use them when there are percentages. in the word problem. So they'll say, hey, you have a population of 50,000 people that come to this town, and the population is decreasing 7% every year. And so you've got a percent built in there. And so that's where these guys come in. So as soon as percentages make their way into the problem, you're changing gears just a little bit. Now, if you notice, both of these, this A of t, A just means amount at time t. That's what this A of t is. A is the starting amount. That A in the top and that A in the bottom, they're the same A. Okay? Notice we both have ones, but the difference is here I have a minus r, here I have a plus r. So if I'm adding a percentage, which that's what r is, we'll talk about that in a second, but if I'm adding it, this is going to indicate that I'm a growth, that it's growing. And if I'm subtracting it, it ends up being a decay, because anything bigger than 1 plus some amount is going to get me bigger than 1, right? That's going to indicate a growth. 1 minus some amount, it's going to give me a number between 0 and 1, that's going to be a decay. So I have to look at the wording of the problem. It may not come out and say, hey guys, I'm a growth, or hey, I'm a decay, but it may say something like, your bank account is, appreciating at a rate of, and it's not like we appreciate you, it's appreciating, it's gaining money, and you have to know that's a growth. Or you buy a car and the value of the car depreciates means it goes down. And so they are going to use words like that, and you kind of have to get a feeling from the problem. Is this a growth or a decay problem? Now, R is that percentage. R is some sort of percent growth, and you're going to have to change this percentage to a decimal. So let's talk about that really quickly, because that seems to be sometimes the hardest part. So let's say I have 6% growth or decay. It doesn't matter which one. I need to change this to a decimal. So the decimal point where the 6 is right there. And to change it all the way to a decimal, to get rid of that percentage, you're going to bump it back 2 spots. 1, 2. That's where my new decimal goes, and you're going to pop a 0 in there. So this is equal to 6% is equal to 0.06, right? 6 cents on the dollar. So be careful, because some people will go, ooh, 6% is 0.6, which is not right. That's 60%. So you have to be very careful and make sure that wherever that decimal place is, and sometimes it's like 1.24%, and you may have to bump it back 2 times, and you need to include all those pieces. You can't just start rounding and stuff like that until the very end. Okay, so if they give you 1 point and they give you some other decimal places, you need to include those in your number. Okay, so we're looking at changing the percentage from the problem into a decimal, because then I want to either add it to that 1 or I want to subtract it from that 1, and I'm going to create a number. Now, again, we seem to have trouble with the simplest things. I'm going to highly, highly encourage you to put these values together and simplify them down into one number. One number. You're going to turn in homework to me, and it's going to say 1 plus 0.57. And I'm going to say, you're losing a point because you didn't simplify that addition problem. Okay. One of the other things that I've noticed is you're going straight into plugging in values. You're not even writing the equation. You're not putting in variables. This t right here will remain a t until I tell you, and t usually stands for time, how much time has passed, and then you plug in a number. So if you are not writing me an equation, you're going to be losing points. And it's as easy as just making sure you have 1 with variables, and usually it's this piece, a of t equals, a will be filled with a number, 1 plus r will turn into a single number, and there's a t in the exponent. And this needs to be an a of t equals, a will be a number, times 1 minus r will be a number, and then a t will be in the exponent. So I need you to be writing me an equation, and there are 2 parts in your homework. So there's a part where, hey, write me an equation, and then, hey, do something with the equation. And if you are not doing them separately as two different types of things, you're trying to just jump straight to the plugging in, you're going to miss the first part. So make sure that you are doing both pieces. You're writing me an equation, and then you're using that equation to give me a value. Now, you definitely need a calculator today, so make sure you have your graphing calculator up, because we are going to be plugging things in. We are going to have decimals. We are going to be raising things to powers. It's not going to be super straightforward, and so we are going to rely on our calculator to just kind of crunch those numbers. Okay, so make sure you have that handy. All right, so a population of 40 pheasants is released in a wildlife preserve. The population doubles each year. Write an exponential function to model this population growth. Then we have a part B. This is very much like what's in the homework. Part B says, what is the population of pheasants on the wildlife preserve after 4 years? So we're going to write an equation to answer the first part. Then we're going to use that equation to answer the second part. Okay, so this says doubles. And so this is one of those ones where it was that very first one, y equals a times b to the x, that I recommended you use anytime you see the words half, triple, double, quadruple, something like that. All right, we need a to be our starting amount. How many pheasants did we start with? 40. So there's a 40 that's going to go in for A. B is how is it growing? How is it changing? This is our growth factor. That's what we're multiplying by each time. And so how is it changing? It's doubling every time. So the doubles, which will turn into a times 2, will be our B value. So here's your equation. Y equals, how many pheasants did you start with? 40 times doubling is 2 times dx. Now, let's think back to what I've talked about in past videos. Can you multiply the 40 and the 2? Is that allowed? It is not allowed. You are not allowed to do that. So if you are going to be trying to simplify, you've got to write 40 as 2 to some power. And right now, there's no way to do that for you. So this is the best thing you've got. This is your answer to part A. This is your equation. Now, for the next part was the population, we're just going to plug in 4 years. Now, that's going to go in for our exponent. So we're going to plug that right in there. We're going to do a little bit of work, and you are going to show me what you're plugging in and where. I got another funny math meme that was like, you feel so confident in your answer, and your teacher's like, where's your work? And I don't know, it's like math is math. But yeah, but what if you do it wrong? And if I can't see what you've done, then it's just all wrong. I want to at least give you credit for doing something right. So at least if you're showing me that what you're plugging in where, I can give you some credit. All right, so in this part, if you were like, hey, I'm going to multiply 40 and 2 and then raise it to the 4th power, I can go, whoa, order of operations, PEMDAS. We are doing 40 times 2 to the 4th is 16. 40 times 16 is 640. There are 640 pheasants on the preserve. Make sure I can spell pheasants right. Okay, now you could type it all in the calculator. That works, but at least show me what you're typing in the calculator at the very least. A dust bunny gathers dust at a rate of 11% per week. The dust bunny originally weighed 0.7 ounces. Write an exponential equation that models the weight of the dust bunny. And then part B, that we'll answer later, how much does the dust bunny weigh after 7 weeks? That's assuming that somebody didn't vacuum it up. All right, so from the gist, from the wording of the problem, can you tell, is it an exponential growth or an exponential decay? It's actually an exponential growth because it's gathering dust, so it's getting bigger. We expect it to be getting bigger and bigger, so this is an exponential growth. And because we have a percentage, we're going to use one of those new formats. So we're going to write A of t equals A parentheses 1 plus, make sure that's a 1 plus r to the t. Now, if you use x's and y's, I'm okay with that. X would be where there is a t, y would be where there's an a of t. That's okay. Unless they are giving you specific variables to use. But you need to make sure that you know that this is different than the y equals a times b to the x, just a little bit. Okay, so here we're going to use the 11%, we're going to use the 0.7, and here's where things go. So A is our starting amount. So this is going to be the starting weight of our dust bunny, and that's going to be our 0.7. R is what we call a growth rate. So it's not a growth factor because it's not necessarily what I'm multiplying by, it's just part of it. How much is it growing each time? In this case, each week, right? T is weeks. So we are going to take that percent, that 11%, and we're going to change it to a decimal. So 11%, the decimal's right there. What is 11% as a decimal? 1, 2, so it's going to be 0.11. That is what's going in for R. T is going to stay T because we need a variable in our equation. If we don't have a variable, we don't have an equation where we have two variables in the equation. So we need to make sure we have T here and A of T here. All right, so A of T equals 0.7 times 1 plus 0.11 to the t power. Now here's the part that I find highly frustrating, and I don't know why it won't happen. I need you to add these together. Like, it's not super hard. And like at the beginning, people do it, and then they start forgetting. I need you to simplify that. So 0.7 times 1.11 to the t power. Not a t on the same level, a t up in the exponent. Okay, that's our equation. So even though this has all the pieces, this part makes me sad in the blue box if you don't combine like terms. Don't make me sad. I want to be happy. Here's the bell. All right, so now we're ready to address part B. So we've got our equation. Part B says how much does the dust bunny weigh after 7 weeks? We're going to take that 7. We're going to plug it in right there for T. So I'm going to do 0.7 times 1.11 to the 7th power. Now that can't really play with a whole lot, but definitely going to follow the order of exponents. 1.11 to the 7th power. And then I wouldn't even like round that. It's got a whole bunch of decimal places. I would just go ahead and multiply that times 0.7. You can also just stick the whole entire thing in the calculator, but you have to do the whole entire thing. So we are going to get and you can give me a couple decimal places. 1.45, our units are ounces. So that's how much our dust bunny weighs. That's probably a pretty fat dust bunny. Okay, so that's the whole thing. We're trying to figure out from the gist of the problem, the wording of the problem, is it an exponential growth or decay? We're trying to figure out the proper format to use. We plug in what we know, and then once we have our equation, then we can use that equation to figure out some answer to a specific question. But you have to write the equation first. You can't just jump into straight, how am I going to get this? The equation is the most helpful part. All right, a 500 milliliter puddle of water is evaporating at a rate of 4% per hour. Write an exponential function to represent the amount of water in the puddle at any given point in time. How much water is in the puddle after 3.5 hours? So, can you tell, is this an exponential growth or an exponential decay problem? This is an exponential decay problem. We are evaporating water. Water is going to go away, so the amount of water that we have is going down. So because we have the 4%, that means we're going to break out that other format, A of T equals A. It's a decay, so 1 minus R to the T power. All right, A is our starting amount. How much water do we start with? 500 is going to go in that spot. How much are we losing? We're losing 4%, but I don't want it as a percent. I want to change it to a decimal. So 1, 2, 0.04 is what I'm going to put in for R. T is going to stay at T, A of T is going to stay at A of T. So you ready to write an equation? A of T equals 500 times 1 minus 0.04 to the T power. Now, again, for some reason this is super hard. I don't think it is. I don't know why. I need you to simplify that. So A of T equals 500 times 0.96 to the T. Okay, now remember it's a decay if our B value, which is what this is now, is between 0 and 1. Do you see how it's between 0 and 1? If I ended up adding, it would be 1.04. That would be something larger than 1. That means my puddle is getting water, and that goes against what the wording of the problem says. So choosing which one, is it 1 plus R or 1 minus R, choosing that is actually part of solving the problem. So make sure you understand from the wording of the problem what's going on. And if you can't tell, you need to contact me and ask about the wording of the problem. It might be something you don't understand, like a business situation, or somebody's buying or selling something and you can't tell based off the words. That's okay. You just need to let me know so I can help you out. All right, they want to know how much water is in the puddle after 3.5 hours. Now you do have to pay attention, especially with the time. Here that we're dealing with this losing per hour, we don't have to make any switches. But if something's happening per hour and then they wanted to know maybe what happens after 20 minutes, then we might have to do a conversion. So just keep that in mind. So you want to compare what the timing is of the problem and then what is the timing of the piece that they're asking you to plug in. So we're going to plug in, we want 3.5 hours. And you can type a decimal up in there. So I'm just going to stick the whole entire thing. 500 parentheses 0.96 to the 3.5 power. And I get 433.43. Now, I really would like, and that's the milliliters, I really would like you to be doing this along with me in the calculator. So if you haven't done this yet, practice typing in the calculator. If you get an answer different than mine, that might just mean we need to look at the calculator a little bit more for you. But I want you to be ready for test time so that, I don't want the error to be you are writing the problem correctly, it's just you aren't getting into the calculator right. So make sure you're practicing that so we can identify any issues that you may be having. But order of operations always. So we got 433.43 milliliters of water left in our puddle. Let's do another one. All right, this one is a little bit different, so we're going to play around with it. We've got iodine-131 is a radioactive isotope used in medicine. Its half-life or decay rate of 50% is 8 days. So that means every 8 days that you have this in your body, right, in your medicine that you've taken, every 8 days there's half of it left. And another 8 days there's half of that left. And another 8 days there's half of that left. Okay? A patient is initially given 25 milligrams of iodine-131. We're going to write an exponential function to represent the amount of iodine-131 in a human body at any given point in time. And then later on, if a patient is given 25 milligrams, how much would be left after 32 days? Okay, so that's our question. So we got to write this, and we're still dealing with a percent, right? We've got a percent loss, a decay rate of 50%. You can also hear it in the word half-life. It's around half. When it's being used up, it's cut it in half. So you could use the y equals a times b to the x because it does say half. If you do, this is 50%, this is 0.5. If you do 1 minus 0.5, you get 0.5, which is a half. So this one you can kind of use both terms. So just want to let you know you're not wrong in doing y equals a times b to the x or doing the 1 minus r piece either. Okay, so I'm just going to go ahead and do this one. We're decaying, so we want to do 1 minus r. And how much did we start with? We started with the 25 milligrams. 1 minus, now we're losing that 50%, so 0.5. Do that now. Here's the difference. We have an extra piece of information. We have this 8 days. So we're going to have a certain number of days, and what we want to do is we want to figure out how many 8-day periods are going to be in whatever time span that they're giving us. So what we're going to do is we're going to do a little bit of division, right? In this 32 days that they're going to ask us about later, how many sets of 8 days do we have? Well, 32 divided by 8 is 4. So we want something to come up, to where our exponent comes up with a 4. So we're going to take our number of days and we're going to divide it by 8. So you can do stuff up in the exponent. There's another one coming up in the EOC review where it's saying how many years since 1980, and so you would want to do a little bit of subtraction in the exponent because you would want to see, well, it's the year 2020, how many years from, are there between 2020 and 1980? You would want to do some subtraction there and put that up in the exponent. So you're allowed to have other things in the exponent, not just t. Okay, so we're going to write this as our equation. A of t equals 25. We're going to simplify 1 minus 0.5. You can do 0.5, you can do 1/2. I'm okay with either. To the t over 8 power. So that's our equation. Then we're going to go ahead and plug in 32. I'm going to do that in a different color. So 25 times 1/2 to the 32 over 8, which we already know is to the 4th power. And then we're just going to stick it in the calculator. 25 times 1/2 to the 4th power is 1.5625, and that is milligrams of that iodine 131. So there's very little, right? Definitely not as much as what they started with, but there is still some left in that person's system after 32 days. So you use some of this stuff in medicine. And then anytime you're dealing with like elements and stuff like that, especially radioactive elements, you have these half-lives. And so some of them are really quick, some of them are really, really long. And that's how they get like, carbon dating for like bones and stuff of dinosaurs. They look at some of the radioactive stuff and the half-lives and those types of things. Your business, Clown at Your Party, purchases a van to drive to parties for $15,000. The value of the van depreciates at a rate of 8% per year. Write an exponential function to represent the cost of the van at any given point in time. So we have a van, but as soon as you drive it off the lot, the value goes down. It's just how it is. Buy used cars, nice used cars, and then you don't lose as much money. It is nice to buy a new car from time to time, but it is true that the value depreciates, and that creates an exponential decay. It's going to go down pretty rapidly at the beginning. So let's see, we have a percentage, so that means we're decaying at a certain percentage. We're going to use A of t equals A times 1 minus r to the t. And I always write this down because I want to have that guidance, that how am I setting this up kind of thing. All right, A is our starting amount. How much do we start? Oh, we start with a value of $15,000. What's our R? Our growth rate, or in this case, decay rate. It's decaying at 8%. So that's going to be 0.08. And those are the two pieces that I need to write this. So let's pull it all together. A of t equals 15,000 times 1 minus 0.8. $1 minus 8 cents is 92 cents. I should definitely have, if this is a decay, I should have a number smaller than 1 in there. If I write like 9.2%, that means the value is going up a lot. So you got to be really careful about what number you put in this 1 minus R or 1 plus R position. We're going to put a T up in here, and then that's our equation. We're ready to roll. We're going to figure out how much the van is worth after 5 years. So we're going to plug a 5 up in the T exponent, and we're going to stick it in a calculator. So 15,000 times 0.92 to the 5th power, and we get, now this is dollars, so you don't keep going with like the cents. Just do 22 cents. We want the nearest penny. All right, so $9,886.22. That's how much our van is worth after 5 years of depreciating value. Let's look at another one. All right, a bacteria colony starts with an initial population of 12 bacterium. They are doubling every 7 minutes. Write an exponential function to represent the number of bacteria in the colony at any given point in time. How many bacteria are present after 60 minutes? Do you think you can maybe at least try to figure out which format you're going to write this in? And if you're feeling really, really adventurous, you might want to go ahead and start writing it. Pause the video, see what you can do on your own. All right, because I see the word doubling, I'm going to use y equals a times b to the x. Okay, if you chose to use the one, it should be a growth, the a1 plus r to the t, you should be adding 100% or adding 1 to that. So you should get the same thing that we get in the end. So A is our starting amount. How many bacteria do we start with? We start with 12 times 2, and then I have this extra piece, the 7. And so that kind of goes back to the iodine thing that we looked at. So every 7 minutes, they're doubling. So I want to take that time and divide it by 7, because then it'll be like cutting it up into chunks of 7s. This 60 is not divisible by 7, so that means that it's going to be like midway through a doubling cycle. So this is going to be x over 7. If you wrote a of t equals 12 times 2 to the t over 7, is the same thing, right? Y and a of t are the same, x and t are the same, pretty much the same position, so you just have different variables, and that's okay. Unless they give you specific variables to use, you can go back and forth with these. All right, how many bacteria are present after 60 minutes? So we've got our equation. Let's plug in 60. So we got 12 times 2 to the 60 over 7. Now you can stick the 60 divided by 7 in the calculator. You might want to wrap it in parentheses. That might be something that I would do, just to make sure that the calculator knows that I'm doing 2 to the 67th and not 2 to the 60. Oh yeah, divided by 7. So there is a difference there. All right, and I'm getting 4,564.97, which we would probably round up to the nearest whole bacteria, right? So 4,565 bacteria. So you can and probably should pay attention, like if you end up with like 4.95 squirrels, please round to the nearest whole squirrel. Things like that. You want to round up to the nearest whole number. Money, you can round to the nearest hundredth because that's dollars and cents. So just keep in mind there may be some rounding components. All right, since 1980, the number of gallons of whole milk each person in the United States drinks each year has decreased 1.15% each year. In 1980, each person drank an average of 26.7 gallons of whole milk per year. That's a lot of whole milk. Write an exponential function to represent the amount of whole milk the average person drinks per year it should be at any point in time. How much milk did the average person drink in 2000? All right, so we are definitely looking at a decay, right? It's decreasing. We have a percentage, so we're going to go with A of t equals A times 1 minus r to the t power. Again, you don't have to memorize that one, but it is something that you need to know. When do you use it? We know the starting amount. We know in 1980 each person is drinking 27.6 gallons. Let's throw our A of t in front. All right, 1 minus, and then we're going to change 1.15 to 0.0115. And then we're also looking at, this is from that 1980. Remember how I was talking about, it's not like of all time, it's like starting in 1980. So we're going to compare, in this case, we're going to look at the year 2000 to 1980. So we want to subtract off of our year. This is going to be, T is going to be our, let me color it. T is going to be our year value that we're going to plug in, and we want to subtract off 1980 because the difference between 2000 and 1980 is 20 years. So we only want to look over 20 years, not 2,000 years. Okay, so if they give you a certain year to base it off of, you're probably going to have that in the exponent. All right, we are going to simplify this again. Please simplify. Please simplify. All right, so it's gonna be pretty close to 1.0115. Okay, so this is going to be, I'm wrapping this up. A of t equals 27.6 times 0.9885 to the t minus 1980. So that's my equation. All right, now let's look at plugging in 2000. So we're going to plug in 2000. We know that there's 20 years apart. I should probably move that more to 2020. So over 20 years, so I'm just going to type in the calculator. 27.6 times 0.9885 to the 20th power. I'm just typing it all in, and we're getting 21.899, so 21.9 gallons of whole milk. And it's just whole milk. So that doesn't mean that we're drinking less milk. We're just drinking less whole milk. So it's gone down. It's definitely decreased over the past 20 years. And that may be, they always tell you about fat content. Why aren't you drinking skim milk? Things like that. But that's probably why it's decreased some. All right, so we're writing equations. How are you doing? All right, that's the last one. So make sure you are paying attention to the wording of the problem. Make sure you're choosing the right format to put it in. Make sure you are writing me an equation and you are getting me an answer. Two totally separate things, but they rely on each other. I know I've kind of taken some points off for the arithmetic and the geometric homework problems because you didn't write me an equation. You jump straight to finding the 83rd term. So I need you to probably go back and look at those and see about making corrections. But that's going to be it for writing our equations. We're going to be solving exponential equations on Monday. And then, guess what? Tuesday you have a test. So make sure you are getting ready for that test. Make sure you're getting your homework done. You're asking your questions. Make sure that you have done your read this before test 7 task as well. That'll get you ready for what's going on in test 7 and what to expect. All right, guys, I'll see you in the next video. Have a wonderful weekend. Bye.